Hello, everybody. Good afternoon. We are here for our third class in the derivation of the Schrödinger equation from first principles, trying to get into the consequences of such derivations. And as I promised to you the last class, in this one I will be showing the stochastic derivation. We have the stochastic derivation gives us a lot of consequences, and I will explore these consequences too in this class. In fact, the stochastic derivation is a nice one because, as I have already said in a previous class, this derivation was not done by me. It was done by two Mexican physicists, Ana Maria Seto, Luis de la Peña, and it's nice to see that even so, I will be able to connect this derivation, this stochastic derivation, with the two derivations that I have already shown to you. And I will do that in terms of physical relations that are very important in the realm of statistical mechanics. So let's go to the derivation. Today, I changed my exposition method. We have a lot of material to pass to you, to show to you. So I think I will spare some time if I present them in the form of slides, PowerPoint slides. So let's begin. I will begin by showing the stochastic derivation. Of course, I am showing a sketchy, in a sketchy way, these derivations. You can find this derivation in a paper that I published in Physical Review A. I don't remember the year. I think it's 2000. Yes, something like that. And in that paper, I present in greater details the stochastic derivation of de la Peña and Seto. Now I will present the main parts of this derivation, the main steps, and we'll focus in the consequences of the derivation and the relation that this derivation plays with the previous derivations. Okay. The first thing that the de la Peña and Seto do is to separate the velocity into two parts. One, which is the so-called systematic velocity, which is just the Newtonian velocity, usual velocity, and also stochastic velocity, which is represented here by U. So, by means of that, the first question that de la Peña and Seto ask is the behavior of these two velocities with respect to time inversion. And it's natural to assume that upon phase time inversion, the velocity, the usual velocity, the systematic velocity, changes its sign. Of course, we know this behavior of the systematic velocity, but since the stochastic velocity is random, it would make no sense for it to change sign upon time inversion. So we have these two situations here, and we can now define a new velocity, composite velocity, which is C line, which is just the value of C, the composite velocity, upon time inversion, which is just this, of course. So this means that we can obtain both the systematic velocity and the stochastic velocity using just C line and C, of course, in this way here. Okay, we are preparing our approach. the mathematics of our approach. Now I will define a variation on the position, and this variation in the position, of course, makes it appear the variable which we are already accustomed to, which is our, for the moment, displacement in Q, in the position. And it, of course, is defined by this displacement with respect to time. Okay, if we do that, we can represent a variation of some function, any function, of course, with respect to time in this way. And look that in this, f is here, so this is an operator that is all operating over f. So we may, of course, represent this by taking the derivatives, and we get this. If you want, you can write this as delta q, and this index I, and here a delta q is I, and a delta q in Cj. And this is just the usual Taylor expansion of the problem. And we are taking this expansion only up to second order. This is the point at which we make the same assumption of the previous derivations, which, as I have already asked you to, I will postpone the explanation of this in terms of the central limit theorem, and I am counting with the application of the charity principle on the part of yours, so that I can continue to present the results without bothering too much with this assumption here. Okay, we have now this expression. I can make, this is also a very important step, very important step. I am taking here an average. I'm taking here an average with respect to these elements here and time, and taking the time going to 0. And when I do that, of course, this does not change this result, but this result, which is delta qi over delta t, with t tending to 0, delta t tending to 0, is just our composite velocity. This is the first connection that we have between the two approaches. This second term here is just a constant, which is just the average of this product here with respect to the variation of time. Okay, so this is just the EJ. I will assume, in fact, they assume that this coefficient here is just diagonal, and so we get the expression that you are seeing here in the bottom of the video. So we may define an operator D operator here, given by the following expression, if of course we abstract from the function f. Okay, so I have assumed the diagonal representation of the D. So I can represent this operator here. Again, it's the same expression as before, just to recollect we have done. And I can, of course, apply the same transformation, time inversion, on the operator D to see what happens. And of course, if I apply this operator here, I get a minus sign here because we have a t here. And we have here the inversion with respect to t. This just doesn't change anything here, but this changes into the C line, the other velocity, composite velocity. It changes with respect to this by the time inversion operator. In this one, I put as a D line because I don't know exactly what it gives to make this transformation upon the expression of D. Okay, so I can use these two expressions to abstract two operators. I have already said that I will do with this one, and now I do that with the same, this other operator here. By making this, I can now represent the first Newtonian with quotes expression, which is just saying that the variation with respect to this operator, of course, which is almost d dt, it goes to d dt if the stochastic velocity is made zero. So I'm saying that this must happen, and of course this happens too. This is just the consequence. They are just consequences of these two equations here. If you put qi here, you will get with a qi here and here, just this term with respect to qi, and of course this term here gives zero. The same thing here for the other equation. So we get with these two terms a term that indeed for composite velocities are relating the change on space with respect to time to these velocities. This one and this one here. Okay. Now I can obtain the systematic velocity and the stochastic velocity by just making a combination, a linear combination of these two results here. This is very easy to say. And we may define this derivation dc, which is a systematic, but I can use S because I will be S to stochastic, and stochastic derivative here. U, the stochastic velocity is just the stochastic derivative upon Q, while the systematic velocity is just the systematic derivative acting upon Q. Up to this point, things are quite consistent. Let's go. Now I want to introduce an acceleration because I want, of course, to go into the dynamics of the system. So, of course, I want to access the construct, the notion of acceleration, because if I don't do that, I can make any dynamics whatsoever. So I assume that the composite acceleration may be represented in terms of the derivative of the composite velocity, which seems natural. But of course, this here is an axiom of the theory. In fact, this approach doesn't separate very well what is assumptions and what are just the developments and consequences, mathematical consequences. So it's not easy to see what we are assuming and what we are just deriving. But okay, no problem after all. So we have this situation here, and we will assume another thing. This is another axiom, which is also reasonable, that is related to the way by which the acceleration changes with respect to the inversion of time. And of course, we will assume that the acceleration is invariant with respect to time inversion. This is obvious because this is important to say, we are making these developments, but we are almost all the time looking at Newtonian physics to see if what we are doing in the limit when the viscosity goes to 0 if the results goes to Newton's mechanics. So this is why we are assuming this property here for the acceleration. But the fact is that if we write this d as the combination of ds and dc, we can do that, and c as the combination of v and u, we can show that our derivative of the velocity, composite velocity, can be written in these terms, these two terms here. But look, to assume that the result is t invariant means that I can relate the acceleration with just these two terms, because these two terms are the ones that keep these t invariance with themselves. For instance, dc changes sign with respect to time inversion, and v changes the sign too. So the application, the operation of dc over v is doesn't change, it's t invariant. The same thing can be said here. It's also invariant, but these two are varies, change sign. So since they change sign, they must be 0 if we assume that the acceleration is time invariant. So these two results are very important in the derivation of the Lagrange set. And when we introduce the dynamic equation, now of course assuming that here we have the composite acceleration, we are in the stochastic realm, we can derive, I won't go into the details, we can express the force in terms of an unusual acceleration, a usual acceleration, and a stochastic term. This point is extremely important for what will come in the fourth class, because if you look at it carefully, you will see that this term here means the Newtonian force. Let's write it like this. And this term here means a stochastic term. And this is just what I expect to obtain, almost everything that I expect to obtain, if I write a Langevin equation. So in some sense, this equation here gives me a hint and a hunch that this approach may be connected to the Langevin equation in some way. So I have two equations here. I have this equation here and this equation here, and I know the expression for the d's, and I can write these expressions in terms of the expanded written expression of these operators. I will assume that f0 is a potential function, derives from a potential, and assuming that, I get these two equations here, which are very complicated at first sight. But I will show that these two equations encompass the Schrödinger equation. It's very difficult to see this at this point, but I will manage to show that these two expressions here encompass the Schrödinger equation in some way. And to show that, I will have to make some simple algebraic operation here in these two equations. I can write this equation, the first equation, in this way, and the second equation I can write in this way. And here I begin to see, of course, I know where I I'm willing to go, I begin to see in what ways I can find the Schrödinger equation, because here it seems that we are getting this term here. It seems, but I'm not sure, of course. Okay, in here we will have this one. We will have just some sort of fluctuation term. But let's go a little bit more to see if this is actually the case. So we now will write the velocity, the systematic velocity, as a gradient of a function s, a low, small caps s, and I will assume that u, the stochastic velocity, comes from a gradient to. This is a constant. A gradient to. These, of course, are another assumption, two assumptions for the approach. As I have said, this approach has a lot of assumptions. And if we do that, the equation that we are looking here simplify to a great extent. And I would like to, at this point, show that here I have something like u is d0. The gradient, I will put these two into this gradient, and then the exponent of r, and I know that r squared is rho, so I have just this thing here, which seems to connect our velocity u with the derivative of the entropy. Here, the entropy with respect to x, the gradient here. Okay, but let's go a little bit further to see that. So when I do that, I can write these two equations. Now I will assume these two values for d. Now, Ana Maria and De La Peña are explicitly searching the constraints that will take these equations into the Schrödinger equation. They assume that we should, to get the Schrödinger equation, we must assume lambda equal to 1, d plus equal to d0, which means that eta plus is equal to 1, which is here, and d minus equal to 0, because we are assuming that eta minus is 0. So if eta minus is 0, d minus is 0, d minus 0 cut here, and also cut this term here. Lambda is equal to 1, and we get this thing here. Let's see. Okay, now if one looks carefully into this equation, we have almost derived the Schrödinger equation, because now I can, using the same ansatz that I presented in the last slide, which were these two, I can simply write this equation here as this equation here. So if I assume that d0 is just h bar over 2 times the mass, I will get exactly at the second equation that I obtain when I am doing the other derivations, the characteristic function derivation and the entropy derivation. And this second equation, as I have told you before, is just the continuity equation. You can see that if you multiply all the terms by r squared, so you have r squared, it gives an r here, gives an r here, and gives an r squared here. I can put this r here 2 times r replaced by an r square. And I can also change this one by an r square. So I have here the derivative of with respect to time multiplied by, we don't have these 2 anymore. So we have just the gradient of r squared, which is rho, gradient of s, plus r rho, which is r squared, the Laplacian of s, lowercase s. Here is just the divergence of s over m. Of course, there is an m. So equation just gets this one here, which is just the continuity equation. So this first equation is just the equation that we have derived. The second equation is just the continuity equation. And we have seen a lot of times now that these 2 equations are equivalent to the Schrödinger equation. If, of course, we write the Schrödinger equation, psi as the amplitude times a phase factor, because psi is a complex function. Okay, so this ends the derivation of the Schrödinger equation by means of the stochastic approach. The fact that we have assumed these things here is the assumptions that will take us into the connection between the 2 derivations. Indeed, I will show this connection by, remember here the result. We have the stochastic velocity connected to this term, which is, of course, can be written in this way. And so the flux of stochastic velocity is just the Laplacian of the entropy, which, of course, can be written the Laplacian of logarithm of O. This Boltzmann's constant, I'm assuming that it's 1. So this is the fluctuation term that we have just derived. So the stochastic velocity is here, and this is the fluctuation term, except for some constants and some physical constants. And what I get here is just, remember that inside the S there is a KB and rho, but I am assuming that KB, the Boltzmann constant, is just 1, just to avoid having to tackle this kind of terms and cancellations. So these terms exactly this same here, and we have, as we have already shown, we also have that C is just delta Q, delta T, if delta T going to 0. So we have a full connection between the 2 derivations, and we, in these terms, can connect. Now we may, how can I say, we may embrace, we may assume all the constructs that are present in the stochastic derivation, that is stochastic velocity, fluctuations, random behavior, the fluctuation dissipation theorem, dissipation is also present in this approach, and other elements of the approach. And this gives us a very powerful tool to interpret quantum mechanics, as we will see in the following. Okay? By means of these equalities here, connections, I can, of course, write my characteristic function in terms of these 2 terms here. And remember that this one is just the logarithm of rho, as we have already shown before. So the two approaches are exactly the same, with the exception that in this approach here, the characteristic function derivation or the entropy function derivation, I have to manage just two axioms. And so I can control much more the appearance of the other constructs in the course of the derivation. And as I have said, this is very important for us because by controlling the symbols of the theory, I can control the interpretations. And by means of that, I can avoid some strange, if you may, interpretations of quantum mechanics, such as many word interpretations and something of the sort. Okay, let's now go to assume the fluctuation dissipation theorem, which is a result or usual of the realm of stochastic approach. We may show that by taking the derivative of the average of Q, delta Q, is the stochastic velocity, which is related. This is a usual theorem of statistical mechanics, which is just related to the gradient of the entropy and related by a constant here, in fact, a tensor. And this tensor is just the expression of the fluctuation dissipation theorem here. Okay? So, in fact, we assume that we are in a realm of a theory that presents a fluctuation dissipation theorem. And this fluctuation dissipation theorem gives us the hint that we may have our equation as one dimension, only one dimension here, to simplify matters, plus a fluctuation term here, which is just a Langevin equation, in which this result comes together with the very expression of the theory. Okay, this is the fluctuation dissipation theorem. I will be back to this theorem in the 5th class, in which it will appear quite naturally. Okay, I have already said that. A last connection between the two approaches is the connection that I can make with the C and the two terms that appear, for instance, in the entropy derivation. They are connected in this way. This one here is just the logarithm of rho, with some constant, it doesn't matter. And here is just the gradient of S is just the average P. The average P over M, of course, we can cut here. The average of P with respect to M is just the systematic velocity, which in my approach, it becomes clear that this is an average velocity. Average velocity, and not instantaneous velocity. This is so because in my exposition, in my derivations, this comes naturally with the derivation itself. Okay. Now we can go to the next interpretation, in the first interpretation issue that I have already addressed in some class, and the last class, if I'm not mistaken, which is the origin of the stochastic behavior. Because, look, we are here in some context like this. We have, for instance, a hydrogen atom, which has an electron and a proton. And we are in the, remember that we are in the corpuscular approach. So we must interpret the hydrogen atom as we always do, as an electron that is, in some sense, moving around the nucleus. This is what we think when we write the Schrödinger equation for the hydrogen atom, despite we like to say in other ways, otherwise. Okay, but if this is the case, where do the fluctuations come from? Why is this? Of course, my particle is doing a very complex movement here. It is a random movement, so it may be performing very strange, very random trajectories. So, what makes this trajectory to change and not be just what we get from, for example, the Bohr-Sommerfeld rules, which are ellipses? Okay, we have two answers for this question. One, which is given by all the people that usually works within the stochastic approach, quantum and not quantum. And we can answer this question in terms of two possibilities, in terms of open systems and in terms of closed systems. The people working in the stochastic interpretation of quantum mechanics and stochastic approach to Newtonian physics and so on, always assume that we have an open system. And these people will almost always connect the external field, because if the system is open, of course, there is something outside that is changing the system. And they assume that this overall electromagnetic field is just the background electromagnetic field that fills the space, which, in my opinion, is highly controversial, to say the least. But okay, this is the way they assume that the stochastic force appears, because, well, something that must be causing the fluctuations and the random behavior to appear, okay? But if you look at our previous derivations, and I will stress again the fact that we have a very clean and neat derivation, that is a derivation with only two axioms, we see that we are not assuming any sort of external source of energy, force, or whatsoever. We are, of course, assuming that we are, these derivations, we are assuming always that we are within a closed system. So in the present approach, the hydrogen atom, well, any atom, the harmonic oscillator, and any other physical system in the realm of quantum mechanics is just a closed system. But if we say that, we now have the burden to say again, where do fluctuations come from? The usual stochastic approach sustains that it comes from the background radiation field. I can't use the background radiation field because it's external field, and an external field cannot be used here. And so I have to look at the situation and see how a closed system may cause within it fluctuations. And now I turn to some expressions, some statements that you can find in the book of thermostatistics, Kalin's book in thermostatistics, which is this one. The equilibrium state, when you look at a system, you may you may think that it is in equilibrium because you see something somewhat homogeneous in terms of macroscopic view. But what Kalin says to us is the equilibrium state is static from the viewpoint of classical thermodynamics is necessarily dynamic. Local inhomogeneities continually and spontaneously generate only to be attenuated and dissipated. Local inhomogeneities continually and spontaneously generate only to be attenuated, dissipated later on. The second statement of Kalin's is this one. For this to happen in this kind of physical system, you may have, in fact, two systems together, and in fact, two subsystems, subsystem 1, subsystem 2, in such a way that the subsystem may, in fact, be a small portion of a larger system, the remainder of the system constituting the reservoir. In that case, the fluctuations are local fluctuations, if within a normally homogeneous system. That is, you see the system, you think that it's homogeneous, but if you look carefully in the macroscopic scale, you see that local inhomogeneities, that is, fluctuations, are appearing and generating spontaneously. So, of course, this seems to be our way out of our conundrum, that is to have closed systems with fluctuations. And this is very usual in classical thermodynamics and classical statistical physics, because we know that what is being said here is just the canonical approach. So if we are right with respect to our interpretation, quantum mechanics is related to a canonical approach in which we have two subsystems when we look at the system, the whole quantum mechanical system. And what subsystems are these? Let's see again the example of the atom, but I stress again that this reasoning can be extended to any quantum mechanical system in any situation at all. So we have an electron here circulating, but not with so beautiful trajectory here. We are assuming something like that. But what makes, and this is the point, what makes this electron to behave in such a random way? The fact is, and I have already said that between the electron and the nucleus, let me write this in this way, for an electromagnetic interaction to be happening here, we must assume that these two electromagnetic elements are exchanging what we call virtual photons. So, in some sense, since these photons travel with finite velocity, this argument will be impossible if the photons travel with infinite velocity, okay? But since they travel with finite velocity, at some time, I will have some amount of energy in the field and some amount of energy in the particle subsystem. So I have two subsystems. One subsystem is related to the field. The other subsystem is related to the particle. But I am interested in describing not the behavior of the field. which in quantum mechanics, I just assume that is almost constant. I assume that we are in the realm of mean field theory with respect to the electromagnetic field. But in the real situation, of course, we have variations in the energy of these two subsystems. Sometimes the energy of the particle being higher, sometimes the energy of the field being higher, and of course, vice versa. And this is the origin of the fluctuation here. The system that can be assumed as nominally very quiet and well behaved, in fact, is a very dynamical system, a very complex dynamical system with very complex trajectories, random trajectories. And in fact, when I look at them, when I keep looking at them, this is important, that I'm saying that I'm looking at them within a time window, if I'm looking only to one single system. What I see is just the fulfillment of the configuration space, in this case, which is a cloud, a very well-behaved cloud here. Look what happens if I continue to behave this way. I will show this behavior for you when I simulate the Langevin equation of quantum mechanics that I have derived in the 2012, the year 2012. Okay, this is the origin of the stochastic behavior. So we have, again, a field subsystem. The field subsystem is being considered as our reservoir. And we have a corpuscular subsystem, which is the system under investigation. We are looking, in fact, to the corpuscular subsystem. If you want to look at this more carefully, our solutions of the wave equation, of course, takes into consideration the potential, but the solutions are related to the elements that constitute the ensemble or the physical system, which are corpuscular in this interpretation, okay? So our field subsystem is the reservoir, I have already said that, and this is the origin of the fluctuation in this approach, okay? Our psi, then, I have already said that, is related to these, the behavior of these elements of the system. So the referent of the x is just the position of the particles with respect to time. And the referent of this one is the statistical behavior of the system along a time window, or the behavior of the system as an ensemble. I will just get to this question between ensemble and single system in the next slide. Okay? So this is what we get in this interpretation to explain the appearance of stochastic behavior or a random behavior within a nominally homogeneous system, such as the hydrogen atom, the harmonic oscillator, and any other physical, quantum mechanical physical system. Okay, so let's turn our view to the fact that now and just now, we can try to connect our views about ensemble, which we are assuming that always apply to quantum mechanics because of our axiom. This symbol here, which is the joint phase space probability density function, is related in this equation to an ensemble. There is absolutely no doubt about that. But since we have now discovered that our system is random, It may be the case that a single system average is also suitable for describing these systems. Let's look at this possibility now. And we have, in fact, in this situation of ensemble and single systems descriptions, a very ancient discussion. Quantum mechanics has brought these two ways of description in sort of battle between Heisenberg, which defended the single system approach, against some, for example, Ballantyne, which was mentioned in the first conference of this school. And Ballantyne defended a position that the quantum mechanics applies only to ensemble, while Heisenberg defended a position that quantum mechanics applies only to single system. What we will show now is that because quantum mechanics has within it a random behavior, it may be the case that it applies the two descriptions apply. Okay. In fact, so we have these two sides of the controversy, and for us, there is no controversy here. There is no controversy here. We have, in fact, a possible equality between the ensemble type of averages and the single system type of averages. And what connects these two averages is just the ergodic principle. Let's see how this is done. So we have the Liouville equation, of course. The Liouville equation applies just to ensemble. I have already said that. And we are trying to see if look into the physical systems can be derived, assuming a single system picture of them. That is, without always assuming that we have an ensemble of equal prepared hydrogen atoms or harmonic oscillators, we can assume that we have only one hydrogen atom. But of course, we can do that. I have already said this. But we can do that in special circumstances. And this will be the key to unravel some elements of, for instance, the Schrödinger cat paradox, and show that there is no paradox there after all, and no weirdness too. So when we are in the realm of a stochastic approach, our objects that are corpuscles or particles perform what we call realizations, and these realizations are just movements which are random. These are movements, okay? And we can make a copy of the system, equally prepared system. Of course, since they are making random movements, this copy will have a different pattern, this realization from this one. And we make also this one. And in fact, we make an infinite number of copies. And if we want to make an average from some experiment, we must measure at some instant of time. For instance, what we are willing to measure, for instance, position, if you will, and we must measure each system of the ensemble at the same instant of time. Please be very cautious with this, because this is the key for the interpretation of the Schrödinger cat without any paradox. In an ensemble interpretation, we are always making averages, keeping the time constant. When we change this kind of average by a single system average, of course, we must make our interventions into the system, our measurements, along the timeline. So of course we can be in one single instant of time, because with one single system, one single instant of time and one single system, we cannot make any average after all. So we have to make a number of interventions in the system, experimental measurements, and this is what we call a time window. Time window. And this means that the time structure of these two approaches are very different. This one we have, for the ensemble average, we have just a single instant of time, while in the single system approach, we have a window of time. Okay, this is just the ensemble approach, the time approach, single system approach. And what connects them is that for some systems, it's not true for every system. For some systems, that applies the ergodic principle, which states that to make these averages gives exactly the same result as to make these averages here. But the fact is, and this will be very important for the interpretation of the Schrödinger paradox. Sometimes, if the situation always, in quantum mechanics, the situation all applies to ensembles. We have already shown that by the very derivations, the path derivations of the derivations that we have made. In some cases, and I will show you which cases are those, you have the ergodic principle applying. And not always, it will not be always. If you have these, of course, we are assuming at this point, I will show you by simulations that this is indeed the case, but at this point we are assuming the ergodic principle. And in this case in which the ergodic principle applies, we have, of course, an equality between single system and in an instant of time, and an ensemble in a single instant of time, and single system along a time interval. Okay, this is the ergodic principle, which makes the two ways of calculating averages equivalent. Whenever, I will stress again, the ergodic principle is applied. And I will show that this is not the case with the Schrödinger cat. And this is not the case, for instance, with the double slit interferometer. Okay? Let's see first with the Schrödinger cat. In this experiment, the Duncan experiment that was proposed by Schrödinger, we have here some apparatus that can trigger another apparatus which has a hammer that can break a vessel with venom, and there is 50%, for instance, can be another probability, but we have a 50% of chance of this apparatus triggering this one and just delivering the venom to the cat. So what we will say, and this is the way the experiment is posed to anyone that wants to understand it. And this is the way by which we are assuming that this is a single system. So we are assuming that the single system approach is valid for such a situation. But the fact is that, of course, we can look at this same problem by means of the ensemble approach. And by means of the ensemble approach, what we have is an infinite number of equally prepared cat systems, the same system, of course, with the same initial conditions. This behavior here is random. And for such a situation, we will have one CAT system, the second CAT system, the third CAT system, and there's an infinite number of CAT systems. And when we look at this expression here, we cannot say in the realm of the ensemble interpretation that we have cats at the same time, dead and alive. Of course, in this ensemble, we will find cats here very alive and cats here dead, alive. In what this expression is saying, that some parts of these elements of the ensemble are being represented by a dead cat, and another part of it is being represented by an alive cat. Of course, we can show the three possibilities we have. This possibility here is related to the probability of finding a dead cat in a number of elements of the ensemble, which is just the relation between the total number and the number of dead cats. And the same thing here for alive cats. And here we interpret this as the correlation imposed upon these situations by means of this random system here. Of course, if you integrate this expression that we have here, this is the expression for a whole. O dead plus 2 squared, O alive, and this term here. And if you integrate this, since we are assuming that the dead situation is orthogonal in the space of the probability density functions, amplitudes, orthogonal to the alive cat, the function representing the alive cat, we just get for whole C1 squared plus C2 squared, which is 1/2 plus 1/2, which is 1. Of course, I'm integrating over all the systems. So, from the point of view of the ensemble interpretation, there is no problem after all of interpreting this one without having to assume that we have cats in some sort of well, how can I say that, zombie-like situation in which they are not dead and alive, and they are expecting us to observe them to become dead or alive. Please do me a favor, okay? But if you assume that this psi function is related to only a single system, then you have no way out as to interpreting the possibility that the cat is alive and dead at the same time. You have no possibility outside this one. And this, of course, is what makes the problem a paradox. But what I will try to show you now is that you cannot assume that. You cannot assume an interpretation based on a single system in this kind of problem, in this kind of physical situation. Because in this kind of physical situation, the ergodic principle does not apply. And the ergodic principle does not apply because this is a sort of a destructive experiment. Assuming without the need of religion, that whenever you get dead for the eternity, you cannot use a single system to make to repeat your interventions in the system in a way that you can measure the cat along the line, because when the cat dies, it dies. and it will come to life again, so you can repeat the experiment with the same situation before. This kind of time structure of such a kind of problem breaks down the relation between the ensemble and single systems. You cannot apply the single system approach here, and so you cannot interpret the situation in these terms. The fact that the two main approaches of quantum mechanics insisted in their positions regarding ensemble and single systems, in fact, is the origin of the paradox here. There is no paradox whatsoever with this situation. And this, you can say, because you are making an interpretation of quantum mechanics that surpasses the distinction, the schism between ensemble and single system approach. Another example of this situation is with the double slit, in which we have exactly the same conclusions about the pure electron. In this case, we have a slit with two holes. I have already said that we can interpret these in terms of ensemble of particles. I have said this in some class, I don't know what, and I won't go into the recollections of that. And of course, in terms of particles and ensembles, the interpretation of this experiment is quite obvious if you assume, of course, exchange momentum, quantized momentum exchange. Okay, here you must have an A here, for instance. So if you assume something like that, you can easily explain the quantized structure that you get into the screen, because this quantized structure here is just a representation of the quantized way by which momentum is transferred from the slits to the particles and particles to the slits. Okay? Okay. So it's nice to interpret in these terms, because here you have points like elements, discrete elements, and here you have discrete points in the screen, on the screen, in the detector screen. On the detector screen, you find points. So you have not to assume that for a single element here, now we are moving towards the single system interpretation, this element here, which is a wave now, or something like that, interacts with itself in such a way to produce an interference pattern here. But of course, since it is one element, and for each element that we throw and make it pass through the slits, we have only one point in the screen in the experimental result, of course. We don't have a interference pattern for one system that we send. We send. So you have to assume that something has happened here to make this wave, which is an extended object, to get to an object or a picture that is just a point on a detector screen. Okay, this postulate here is the so-called postulate of escaping me now, wave-packed projector. It's not this name. I will find the name in what follows. Just take a moment, I will remember. So the reduction of the wave packet, reduction of the wave packet. This is a postulate of the usual interpretation of quantum mechanics, because if you have a structure here that is extended, and you always get just a point in the screen, something has happened here to make this extended structure to appear just like a single point. Okay, in this approach, in terms of ensembles, the result is not the exchange of energy and momentum between the particle in itself. It's the exchange of energy and momentum between the particle and this slit. In whatever slit it passes. Okay, and this is happens because we have, of course, in this case, symmetry. And this symmetry, whenever we have, it induces quantized exchange of momentum according to the Bohr-Sommerfeld rules. Okay, very nice. We have just an ensemble approach. But why we can't assume here a single system approach? Because here again you have a destructive experiment. If you send some element here, doesn't even bother if it is a particle or a wave. You have an entity here, and this entity comes into the slit screen, and then it hits the detector screen and changes into a point in this detector screen. The experiment, the single system experiment, has ended. You cannot recover the same situation, except if you make an ensemble approach. You cannot recover the initial situation to keep looking into a single system. So it is the insistence in interpreting this system in terms of a single system approach, that makes it appear the paradox, which is here not viewed as a paradox, but it's exactly the same thing of that appears in the Schrödinger cat, of a wave that must be reduced in some sense to appear in the detector screen, on the detector screen as a point. Okay, so this is the same thing, and it comes from an insistence of force the single system interpretation into a situation in which the ergodic principle does not apply. So, since quantum mechanics applies to ensemble, it is guaranteed by the derivations, only the ensemble approach should be used here to interpret this experimental situation. And in no possible case, this single system approach. If you do that, you get no paradox, no weirdness whatsoever. Okay? This is different if you have, for instance, a hydrogen atom, again, the hydrogen atom, but it could be the harmonic oscillator. In this case, you have the particle making the very complex trajectory around the nucleus because it's random. And in this case, I have already explained that you have exchange energy and momentum between the nucleus, between the particle subsystem, which is electron protons, and the field subsystem. And this is the origin of the fluctuation. I won't come back to this explanation again. And having these two elements, what we can say that in this kind of system, you can, for instance, make some experiments that preserve the system in the following way. Let's assume that we are trying to find the position of the electron in the atom at some instant of time. Of course, we can do that assuming an ensemble of hydrogen atoms. I won't go back to this. But if we are using a single system, what can we do? We must assume a time window. So we make a non-destructive experiment. We make our measurement. We wait the atom to get back to its original situation, so our experiment cannot be destructive because of that. And when the atom returns to its original situation, we make the same experiment again. So what we are doing, we are keeping one single system, and we are making experiments on this single system within a time window. Okay? In such cases, the ergodic principle applies. At least it is our assumption that it applies. And I will show you that it applies in what follows in this course. Okay? And here we will have no kind of paradox by assuming that you have a single system and an ensemble. You have nothing of the kind. Okay? So let's see how can we interpret the Heisenberg special relations. Before I do that, look that we are now investing into quantum mechanics by presenting a number of interpretations of usual expressions and situations, because we have already walked through a long path. In such a path, we have found the characteristic function, the entropy, fluctuations, random behavior, stochastic simulations, and stochastic behavior, fluctuations again, the fluctuation dissipation theorem, etc. So we have a lot of elements that can be interpreted and that already are interpreted because of the derivations that we can use to interpret the other elements of the theory. This is why we are trying to make some number of derivations of the Schrödinger equation, because each one of these derivations is giving us a number of constructs or symbols that we can now use to interpret the other elements. And the Heisenberg special relations are an example of that. I have already talked about that. I will briefly come back to this issue. We have in one of our axioms this expression, and this expression, of course, is taking no problem. Eu posso falar? Well, sorry for the small breakdown in our presentation, but let's come back to our exposition. Okay, so I was talking that this expression was one of the axioms of the derivations, the entropy derivation, and in this expression I have an equal sign. And here, when I integrate this expression, I get the usual Heisenberg relations, which comes with greater than or equal sign. In fact, if you look at the usual calculations, you see that this expression comes directly from the fact that x and b do not commute. Okay? So, what you are abstracting here, it's very important to understand that, what you are abstracting here is the state. You are not fixing the state of the physical system. And this is why you get the greater or equal. It has nothing to do with experimentation and elsewhere. If you assume a definite state, what you get is always an equal sign, always an equal sign. And an equal sign, as I will show, blocks the usual interpretation in terms of error or in terms of uncertainties. In fact, in this case, for instance, for the oscillator, harmonic oscillator, for each state of the harmonic oscillator, you have the Heisenberg relation equal to n plus 1/2 the Planck's constant. If you Planck's constant here, the energy has a value. So if you assume now, try to get this same view to this situation. Prepare an harmonic oscillator in a state n equal to 1, and then let us make the same kind of experimentation here. Let's make an experimentation using a very accurate laser, and let's make the experimentation using a stick. If we assume that quantum mechanics has anything to do with this kind of situation, the experimental situation, we are saying here that it doesn't matter if you make the experiment with a stick or with a laser. You get exactly the same results because you have an equal sign. You are not free to say that, oh, now you with this stick you have a much larger value for this expression, while for the laser you get so close to h bar over 2. This is completely wrong, completely wrong. And this is why the equal sign blocks the usual interpretation of this inequality in terms of, and also equality in terms of some sort of experimental error. In the present interpretation, what this equal sign means is that each state of the system has a definite fluctuation signature. And this is even more explicit here in this expression. We also have an n here. Because the system fluctuates in some way or the other, you have a fluctuation structure given by an expression based on the state of the system, the quantum state of the system. Okay. This is what we call an extrinsic interpretation, because it relies on an external relation between the system and something outside it, for instance, an observer. And this is deemed to fail because in the Schrödinger equation you don't have the variables of the experiment. You never have the variables of the experiment. This means that you may change the variables of the experiment using sticks and accurate lasers and still getting the same result. And this makes no sense, no sense. In this interpretation, by means of fluctuations, we don't have anything outside the system to explain the fluctuations. The fluctuations for each state represents, in fact, the signature of the state. And this is an intrinsic interpretation. Okay? This is the difference between the two. Okay, so I will briefly touch this situation here. I have already presented these two images. This image here is the contours for the Bohmian situation. You have here the Hamiltonian in Bohm's approach, which is just that. plus 1 plus x squared over x squared 2. And this Hamiltonian gives the equal energy contours like these ones. And these are the contours of the probability density function that we have just derived by our derivation of the Schrödinger equation. I have already showed this to you. And you can see that there is a great resembling. They are greatly resembling each other. Okay? What we show here is that if you have a small variation in x in this place of the configuration space, you will have large variations on the momentum, because exactly of this term, which is a fluctuation term in our approach and is a potential in the approach of bombs. But in our approach, if you are close to the origin, you will have large fluctuations, while for the position fluctuations, you will have small fluctuations. Here you have some sort of equal fluctuations. It's close to 1/2 here, in fact, which is the fluctuation for the ground state. In fact, this is so because if you draw the usual classical situation, you will get something like that for this problem. Okay? So what quantum mechanics is giving us by means of these terms like this is the kind of the structure of the fluctuation that is going on within the physical system. And this is unrelated to external observers and anything of the kind. Okay? This is how we interpret this in this approach. I will briefly say about talk about the time-energy relation. I remember that to you that we are talking in single system by time window, and this is represent fluctuations on the energy. And how we interpret this relation, which is the usual time-energy relation, is not by saying that there is some periods in the system and we try to make the connection between such periods with the amount of energy of the system to get something like that with an equal sign. What we have here is that first, there can be no uncertainty in time, because time is a parameter, and you don't have uncertainty in a parameter by definition. So the usual approach is to try to find something that you can connect with time and to show that this relation applies for this element here. In this approach, this is nothing like that. We assume again that we have a situation of a random movement, and in fact, to apply the ergodic hypothesis or the assumption, we have to assume that this system, with its random movement, fills the sample space in a manner that for a time window of this width, you can apply quantum mechanics, you can see quantum mechanics as a single system with a single system approach. Since the ergodic, of course, the ergodic principle will not apply to a time window of this width, because for such a width, the system won't have enough time to fill the phase space in a manner that you can apply the ergodic principle. So this expression is given, in fact, the criterion for the application of the single system interpretation. Okay? And in fact, see that if you have a very wildly fluctuating system, of course you can use a smaller time window, because the fulfillment of the state space, the sample space, will be much quicker than a system that fluctuates in a slower way. And this is exactly what is being said here in this expression. In fact, this expression by means of the stochastic approach is related to the fluctuation dissipation theorem. That means that I don't have the time to show here. And this is exactly the content of the fluctuation dissipation theorem. Okay, thank you for watching. This is what I would like to show you. I made my exposition almost using the same time as those before. And now I'm open to answer any question of yours. Thank you very much. Eu vou entrar aqui nas notas compartilhadas, se meu computador não me barrar. Parece que vai mostrar aqui. Ah, tá quase. Pega. Loading. Do Hensley, né? If we quantify a classical stochastic equation, can it lose its stochastic property? I understand what you are asking, Hensley. If you are trying to see if that statement of the usual approach, that when you see a system, when you look at the system, you change its properties, etc., etc. In this approach, this is not the case. The stochastic equation, of course, the behavior of the system will be perturbed by any sort of observer. But we are assuming that after this disturbance, you wait for the system to go back to its original state, and then make again your measurement. If you are trying to look at the system like as a single system, if it's possible to do that. So the fact that the stochastic approach is fully intrinsic, as I have said. As for instance, you have with the Newtonian approach. The Newtonian approach, of course, if you look at a feather falling, and you use some sort of apparatus to measure the position of the feather, and you have wind and etc., of course this will disturb the system. But Newtonian mechanics has nothing to do with that. Newtonian mechanics is objective because it gives you what happens in the ideal situation. And here the ideal situation is a stochastic situation. Of course, here, as with Newtonian mechanics, any kind of intervention that you make in the system will change the system some way or another. And you may change this system in a way that you can continue to make an experiment on it, or you can change this system in a way that you cannot do that. If you change the system in a way that you can continue to make the experiment because the system comes back to its original situation, then you may treat the system in a single system approach, And the disturbance, you can avoid it by simply waiting until the system restores its state. But if you cannot do that, you have to use an ensemble approach. And both Newtonian mechanics and quantum mechanics assume the same thing here in the present interpretation. That is, the theory has nothing to do with the way we observe it. It gives you the internal situation of the system by means of how it fluctuates, how its behavior is handled by the signature of each state. And when you observe this system, what you measure is just this element, objective element of the system, which is its fluctuation, wherever you want to observe. But again, this approach does not has nothing to do with external observer. It's completely intrinsic. It's completely objective, and it gives the same results of usual quantum mechanics because we have just derived the Schrödinger equation, which is the basis of the quantum mechanics. Okay. Thank you for your question. Okay, I don't think that we have any more questions. So let us finish this class. In the next class, I will show you finally the central limit theorem derivation. Thank you again for being present in this exposition, and see you tomorrow. Thank you very much.